If we truly want to treat AI agents as humans, then they absolutely need to have memory. Imagine if you have an agent that remembers everything about you, that becomes better with experience and time, just like a human. This is what we'll cover in this video, along with many code examples that I will walk you through. My name is Abdullah, and I'm an AI engineer at Microsoft, very passionate about teaching concepts from first principles. So if you want to become a better AI engineer and you're a fan of a no BS approach to teaching, then subscribe to this channel. Let's start from the basics. Large language models by themselves are stateless, so each request or prompt is processed independently, as you can see in this example. So what we do is we engineer short-term memory, which is remembering this specific conversation. And more recently, we started to engineer long-term memory, which spans across multiple conversations. Long-term memory, which spans multiple conversations, became extremely critical. Imagine if you have an AI agent that manages inventory, and you would have to re-explain the supplier information every time you open a new chat. That becomes unusable. So let's talk about these types of memory in more detail. There's two types of memory, short-term memory and long-term memory. Short-term memory means that the agents maintain the entire chat conversation history with you. Almost every popular chatbot that you use implements this out of the box, like ChatGPT. It is short-term because it's specific to this chat session, and the techniques that we use allow us to squeeze as much information as we can into the context window. So in this example here, this is an example of messages such as system prompt, the user prompt, and the response from the agent. We apply multiple techniques like summarization or picking the last n number of messages. The point is we are trying to stay within the context window, and this short-term memory only applies to this specific chat session. The other type of memory is long-term memory, which spans across multiple conversations. So we're truly treating agents like humans. Imagine if you have a friend that forgets everything after every new conversation that you have with them. That would be crazy. Long-term memory is typically implemented using retrieval augmented generation, or RAG, where facts such as the user preferences are stored in a vector database, and with each user prompt or question, these facts are retrieved from the vector database before providing the answer back to the user. So all of the responses are grounded on these facts or memories that are stored in the vector database. We'll get into that in a bit. So the distinction is, one is at the session level or at the chat level, and one is at the agent level. And with the latter, the agent really feels like an agent. ChatGPT actually started to implement long-term memory. It always had short-term memory, otherwise it would be unusable. But recently, you have the capability of actually updating the memory store, or you can even tell it in the chat to do that. Notice that it shows you memory is updated. The focus of this tutorial is long-term memory, because short-term memory is very easy to implement. We've been doing this for years. Most of the libraries or SDKs or packages just do that out of the box. But the real engineering challenge lies in long-term memory, and that will be the focus of today's tutorial. Now, within long-term memory, there are three types of memory. One is semantic memory, two is episodic memory, and three is procedural memory, and I will explain those one by one. First, semantic memory. This stores basic facts about the user, as an example. So maybe you prefer to book aisle seats, maybe you like Marvel movies, or in the example of the AI agent that manages inventory, that could be supplier details. So these are just basic facts. That's the most simple type of long-term memory. The other is episodic memory, or what we call experiences. This is when the agent remembers past actions. It's when the agent says, oh, I remember doing something similar to this. So again, using the example of the AI agent that manages inventory, the agent might say, I remember that when I needed an urgent laptop delivery, I negotiated a 2-day window by mentioning bulk orders, which seemed to work. So the agent actually remembers past interactions that worked and were successful, and they would use these experiences or past interactions to form their responses to future questions. Very, very, very powerful. And the last type is procedural memory, or what we call instructions. So semantic memory is just remembering basic facts. Episodic memory is when an agent remembers past interactions or experiences. Procedural memory is when an agent becomes better with time. So literally, the more you use the agent and the more you give it feedback, the better the agent becomes with experience. It's exactly how we would treat humans. Imagine if you have a human that recently joined your company. Maybe for the first 3 months, they're still onboarding to the role, and they might not be as good as they would have been 1 year or 2 years or 3 years into the role, and that's because they gained experience. And this is what we call self-learning AI agents. These are AI agents that become better with time. That is the ultimate goal. Because again, we want to treat AI agents exactly as humans. So anytime we are trying to engineer AI agents, always think about how can I let the AI agent behave as closely as possible to a human. And I know this sounds cold, and I know there's lots of talks around AI agents replacing human jobs, but just use this as a frame of reference whenever you are engineering AI agents. So if you want to truly treat an AI agent like a human, we know that humans get better with experience. We know that humans don't forget things. We know that humans remember past interactions and they use these past interactions to form their future judgment. So again, please use this as frame of reference whenever you are engineering AI agents. Let's go through examples on how semantic memory, episodic memory, and procedural memory are implemented. So I will explain each one at a high level in terms of how they are implemented from an architectural perspective, and then I will go through code examples. Let's start with semantic memory. So fundamentally, with semantic memory, you have an AI agent. That AI agent has access to tools, just like any other AI agent. So in this case, that AI agent has access to a tool that sends email. It has access to a tool that calls a weather API. And more importantly, it has access to a memory tool. This is basically a vector database that stores basic facts about the user, because again, we are talking about semantic memory. So what happens is that when a user explicitly mentions that they have a specific preference, so in this case, please note that I like Marvel movies as an example, whenever these types of inputs are provided to the agent reads that input, it knows it has access to a memory tool, and it knows that anytime a user mentions a specific preference or mentions a specific fact, or explicitly asks the user, hey, please save this piece of memory that can be used for future references. So either explicitly or implicitly, the agent will understand that request. It would understand that it has access to the memory tool. And based on that, it would decide, okay, now it makes sense to call that memory tool with the input user likes Marvel movies. And then that piece of information is stored in a vector database. And these are examples of information stored in vector database. So user likes Marvel, user prefers aisle seat, username is John. Exactly what I showed you in ChatGPT, they implement this very similarly. So we are storing basic facts and what we call semantic memory in these vector databases. So anytime a new user comes in the future, the agent would look at this request, and then it would ground its responses based on the memory that it has stored in this vector database. So the next time the user asks, what type of movies do I like? The agent can use this vector database to ground its response on that. And the nice thing about this is that because this is stored in an external vector database, so this is outside the agent, it can span across multiple chat sessions, okay? So if the user opens multiple chat sessions, it doesn't matter. It's still talking to the same agent. That's why I call it agent level and not session level. Now let's go through a code example. We're going to build an AI agent email assistant that scans incoming emails and responds appropriately. Let's get into it. So what I do is I import all of the relevant packages. I load environment variables from a .env file. So you need to have an OpenAPI key defined in this format, which we then load. And the first thing that we do is we store basic user profile. So this is all hard-coded in my code, but in a real system, this could come from information that is stored in the session if you're authenticating your users, okay? This is hard-coded in this example. Then what I'm going to have in this code or in this agent is I'm going to have a triager that looks at the incoming email and decides whether it has to ignore the email, whether it has to notify specific team members, or whether it needs to respond. Okay, so I'm just making this a bit more complicated to match real life scenarios. So we're going to have a triager in addition to the main agent. And that triager is going to use a lightweight model. We don't have to use a very expensive model. So I'm using GPT-4o mini in this case, okay? So I'm defining the LLM client that is using this model, and this is specifically for the triager, okay? Next, I define a router class. What this router class does is that it specifies the output that we get from the triager LLM, okay? And we're turning the triager LLM to give us back a response in this format with classification, so whether it's going to be ignore, respond, or notify, along with the reasoning, okay? So any response we get back from the triager LLM is going to be in the format of classification and the reasoning behind that classification, okay? And this is where we define that, or we provide that router as an input to the LLM client. So we are telling it, respond back to us with structured output that matches this router class, which has classification and reasoning as output properties, okay? So far we're dealing only with the triager agent. We're not dealing with the main agent, okay? That is using a different model. Then we define the triage system prompt, and that is using a system prompt template. So we're not hard coding everything, okay? So in this case, we are saying you're an intelligent email assistant for full name, who is blah, blah, blah. So we can change that here dynamically, okay? So we're not hard coding that in the prompt. Again, in the real world, that would depend on the user that is signed in, okay? Hence, we want this to be a bit more dynamic. So the triage system prompt is simply, we're telling it exactly how to analyze incoming email and how to classify them into ignore, notify, or respond. We are telling it to be thorough in its reasoning, etc., etc. Now, you might ask, why did we have to use a router class instead of just defining everything in a system prompt? So we can absolutely, in the system prompt, say, hey, please get back to us with a response in this format. So with the reasoning and classification. Using a router class is a lot more neater because AI is always non-deterministic. You can't 100% depend on the fact that AI is going to give you back a specific response every time, okay? So the neater way to do it is by using a router class from the base model class. So this is inheriting from the base model, okay? So now that we define the triage system prompt, everything has been set up from a triaging perspective, okay? So any incoming email is going to pass through that triage agent and it's going to classify the email and provide the reasoning behind that classification. Next, we define all of the tools that the main agent is going to use. So the main email assistant agent is going to use. So in this case, the first tool is writing an email. Obviously, this is dummy data in the real world. This would implement a real email service API. Then we have a tool for schedule meeting, and then we have a tool for checking calendar availability. So these are all examples of different tools, and we use the tool decorator, which tells LangChain that these are the functions that can be called by the large language model. Okay, so this is what LangChain expects when we define these tools. Now we get to the interesting section, okay? So we import the memory storage system from LangGraph, okay? And the first thing that we create is the store, okay? So we create the store that will be stored in memory. In this case, we're not using a real vector database. We're just using a local vector database stored in memory, okay, just for demo purposes. And here we are specifying the embedding model that we will use, obviously, to turn these memories into embeddings. So we use this OpenAI text embedding module, okay? Then we import memory management tools from LangMem. Now that we define the store, which is the local vector database that is using this specific embedding model, now we define the actual memory, okay? There's two steps to define the actual memory. First, we create the actual memory, okay? So we create that memory in a specific namespace. Think of a namespace as a folder, okay? So the namespace is going to be separated by the user IDs. So you're going to have a folder for each user ID, because obviously we want to store different memories or facts. In this case, we are dealing with semantic memory per user, and that's separated or segmented by user ID. So think of namespace as folders. Each folder is a user ID, and inside each user ID, you're going to have specific facts. Okay, so this is how we will segment our memories from different users. And then we have to specify that this is of type collection. So collection means that this is semantic memory. So we have to tell LangChain that, okay? So that is creating the actual memory, okay? So that will be created in our vector database. We haven't stored anything yet. We are just creating the namespaces or folders and creating that segregation. And then we are creating the search memory tool, okay? So basically what we are doing here is that we are creating a tool, just another type of a tool that our agent will have access to that searches for information in that memory store, okay? So we are telling it to use the same namespace so it actually searches in the right user's memory. And we don't want it to search for another user's memory, okay? So very, very important. Again, we specify that it's of type collection. So far we defined the triager. we defined all of the tools that we need to use in the main agent, including the memory tools, which is creating the actual memory and searching for the memory, okay? This is just printing statements here that just shows us exactly how it goes. I'm gonna run this and show you how it runs. And then after that, we define the main agent system prompt, okay? So this is the main agent. This is not the triager agent. We already defined the system prompt for the triager agent. This is for the main agent. So we are saying you are a full name's executive assistant, blah, blah, blah. Again, this is all using a prompt template, which is more dynamic. We specify the instructions and we say important, use memory tools. So it's very important that in the system prompt, we are telling it to use memory tools to remember important information about people, projects, preferences, and past conversations, okay? So then we define create underscore prompt function, which returns back the system prompt, okay? So the content of that system prompt is going to be this thing that we defined here, and then we access what's inside it by tapping into dot format. The instructions in this case is going to be, so there's going to be agent instructions. So what we defined here at the top, which is use these tools when appropriate to help John manage tasks effectively. And then we provide the profile information, which is the name, full name, and user background that we defined at the top. And then we also add the entire conversation history from the state. So this is what is returned from the function that we will call later on, okay? So then we create the list of tools in an array or a list. So these are all the tools that the agent have access to. And now is the step where we create the main React agent from LangChain. So this is the model that we are specifying. These are the tools that the agent will have access to. And this is the system prompt of the agent that we defined here. Okay, so remember, we are returning this entire instructions that is being filled dynamically inside this function. And then we are specifying the store, very important. That is the memory store that the agent will use to create new memories and search for memories, okay? Then after that, we define config, which is very important. So this specifies which user's memory to use. So we are specifying this specific LangGraph user ID. And typically that would come from user authentication. So if you're implementing user authentication in your application, this would come from that, okay? Then we will test memory storing capability. So what we are doing here is we are invoking the agent and we are just saying Jim is my friend and he works at Google. And then we would test it with another question and say, who is Jim and where does he work? I'll show you exactly how we run this. Very important that in my question, I specify the exact config I'm using, which is for this specific user ID. So we're invoking the agent for the first time and we're invoking the agent for the second time. Then we print all of that. I promise you I will show you exactly how that works. And now we define the actual triage router function because we only defined the triage system prompt, but we didn't define the actual function that is going to do the work, okay? So the first thing that we do inside this function is that we extract important email parts from the state. So state is basically of type dictionary, okay? So this is exactly how the email is going to be sent to us. It's going to be of type dictionary. So that is how the incoming email is going to look. It's going to contain a list of messages as well, or the conversation history, okay? So we're just extracting the important email. So we're just extracting email parts from the state, okay? So we're extracting author, we're extracting to, we're extracting the subject, email thread. We are building the system prompt using the trash system prompt that we defined all the way up top. Again, we are inputting these dynamically. Then we build a custom user prompt that we are hard coding in this case. So we're just specifying an author, a to, a subject, and an email thread that we are defining below. I will show you that in a bit. And then we are invoking the triage agent with the system prompt and the user prompt. And hopefully we will get back a response, remember, with classification and reasoning behind that classification. And here I have a series of if-else statement where if the classification is respond, we actually respond to the email. If it's ignore, we just ignore. And if it's notify, we just ignore. In this case, in the real world, we would actually notify real team members, okay? So now, after all of that, we finally create these agents, okay? So we create the state graph, that's the email agent. We create the first node, which is the triage node or the triage agent. We create the other node, which is the actual main agent or the response agent. And then we define the flow. So basically the start, it starts at the triage router and then it ends at the response agent, okay? And most important step is that we need to pass the store to the email agent, okay? And here, this is just optional to generate a workflow visualization on how that looks. I'll show you how that looks like in a bit. And then we print all of that. This is the email that we are going to test on, okay? And this is how we will invoke the main agent with this email. We get back the first email response, and then we will do a follow-up just to test if it actually remembers the previous conversation. It is a bit of a complicated code, to be honest, and I didn't write this from scratch. By the way, there's a very good course by the founder of LangChain that goes through that in more detail. This is an example of a real-world AI agent that we would build. I know the code is a bit complicated, but hopefully I explained this very basically. Okay, so let's run this. So let's just expand this. Now we have the memory tool information, a series of print statements. Here we are testing the memory. So we're saying Jim is my friend and he works at Google. And then we ask a follow-up question, who is Jim and where does he work? Jim is Joe Doe's best friend and he works at Google. So this actually worked. And then we test the main agent and notice that the triager said that this is an email that the agent should respond to. Hence, the agent will call the email tool. It responds to the first email, which is saying I was reviewing the API documentation for blah, 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 blah. And the AI said that I've responded to Alice's email regarding the API documentation. And then the follow-up email is any update on my previous ask. And the AI says that I've sent an email to Alice requesting more details about her previous request. So the agent remembers past interactions, and that's the main point. I know the code is a bit complicated, but hopefully I've managed to break this down as best as I can. Again, in summary, semantic memory is when you store memory information, and these are basic facts in a vector database. And any question that the user asks will be grounded on these facts that are stored in the memory database. Hence why retrieval augmented generation is used, because the agent is retrieving memory information at every request. And again, because it's stored externally, it can span across multiple chats. Next, we're going to talk about episodic memory. And before we go through a code example, I just want to explain how it works at a high level. Remember, episodic memory is when the agent remembers all of the past interactions and uses all of these past interactions to form future responses. So practically, this is implemented via what we call few-shot prompting. Remember, few-shot prompting is a prompt engineering technique where, as part of the prompt, you put examples of desired outputs. So for example, if we are dealing with an email assistant agent, as part of the system prompt, you can have few-shot prompt or examples of email classifications. So this is what we call few-shot prompting. With episodic memory, instead of providing these few-shot prompts or examples as part of the system prompt, we store them in a vector database for the agent to retrieve them. So the way this works is that whenever a question comes in from the user, the agent retrieves relevant examples of ideal outputs and uses that to form its response. So episodic memory is really practically storing these few-shot prompts in a vector database, so in an external vector database and not part of the system prompt. But the main question is, how do you store these prompts in a vector database? The first method is manually. So if you have a very simple use case, you can have a human come up with ideal examples and store that in a vector database. Now that would only get you very far. For more complex use cases, you can actually do that automatically. And this is a key element of properly implementing episodic memory. The way to do that is by gathering user feedback. So the user would actually mark interactions as positive. And any interaction that is marked as positive is stored in the vector database. So now the agent is going to have a repository of positive interactions that are marked by the user. So any future prompt or question that comes from the user, the agent is going to retrieve positive examples from the vector database and uses these examples to form its response. So this is a more automated way of doing it. Sometimes in practice, AI models are actually used instead of user feedback to classify an output from an agent as positive or negative. But in practice, most of the time, there's a human in the loop, and we capture these interactions or the feedback from these interactions by the user, and we store them in a vector database. That is how it's implemented in practice. With that said, let me show you a code example that goes through all of that. I'm not going to spend too much time covering this code because a lot of the same principles are covered in the previous code example. So what we're going to do is we're going to store basic user facts, exactly the same as before. We're going to define the triager. And then the most important element in this piece of code is where we implement episodic memory. So here we are providing few shot prompt examples to the agent. So in this example, this is an email that we would have to respond to. Okay, so this is what the agent should learn to do. This is an example of a few shot prompt. Of course, we're not going to provide that as part of the system prompt. We're going to store that in a vector database. So in this case, we're doing it manually. Okay, we're not doing it automated, but of course, the same principles apply if you would collect user feedback, and then you would have logic in your application that if the user marked this as a positive interaction, you would store that in the vector database. Exactly the same principles apply. The key element here is to make sure that you store these few shot prompts into a vector database. So we have all of these examples, and then we put these few shot prompt examples into the vector database. Notice that this is different from collection, which is for semantic memory, okay? So we're gonna have unique IDs for each example. Hence, we are generating a unique ID for each example, okay? So this is for example 1. We do the same for example 2, and we put that in the store again. That is pretty much all you need to know. And then we define a function where the input to that function are the few shot prompt examples that we retrieve from the vector database. If we don't have any examples, we just return no previous examples found. If we do have examples, we get that from the vector database. We parse that input, and then we return these formatted examples. And then we follow the same exact logic as the previous code. So we define the router, the triage system prompt, and then we go through all of that. And then we define the triage router function itself, and we build the user prompt, the router, and then the logic of the classifications, exactly the same as before, exactly the same tools as before. We still have semantic memory capability in addition to episodic memory. Okay. Now, if I scroll down, here's what's different. What's different is that in the store, we have these few shot prompt examples stored in that vector database. So we're going to retrieve these few shot prompt examples before we give back any response. So this is where we define the agent, again, exactly the same as before. And this is an example of an email input that should absolutely be classified as response, because this is what we provide in our few shot prompt example or in our training example. We invoke that, and this simulates just adding a new example. So maybe the agent got it wrong and we want to correct it. So again, we grab that example or interaction and we store that in the vector database. So that is added spam email to episodic memory. So that's how we would do that dynamically. So assuming you are collecting user feedback as an example. And then we would test with a similar spam email, and that should now be classified as ignored based on the example that we have given it dynamically. So that is really pretty much it. Let's try to run this. So if I want to expand that, as you can see, we stored 2 example email classifications for the agent to learn from, and then we are testing that, and it says it found 2 similar examples from past classifications, and it did the correct classifications. And then this is the example if we add the new example dynamically, which is the spam email, and it goes through the same process over and over. And finally, let's talk about procedural memory. And before we go through a code example, again, I'm going to explain how it works at a high level. Procedural memory is actually very simple. Remember, procedural memory is when an agent becomes better with time. So the more you interact with the agent, hopefully the better the agent will become. So how do you control the behavior of the agent? That's the fundamental question that we have to ask. And the way you control the behavior of the agent, or one of the simplest ways to control the behavior of the agent outside of altering the parameters or the weights of the model, is actually via the system prompt. So you can have so much control over the agent behavior via just the system prompt. So with procedural memory, what we want to do is we want to dynamically change the system prompt based on the user feedback. Okay, so with episodic memory, we are storing positive interactions or negative interactions based on the user feedback, and the agent is giving back responses that conform to those interactions. In this case, we want the agent to actually change its whole behavior based on the interactions with the user. So the more the users use the agent, the better the agent becomes. Okay, so for example, if a user uses an email assistant agent and they give feedback to the agent that this email should be classified in this way, or this email should be responded in this manner, or I want you to use this tone. You can dynamically store these user feedback as system prompts in the vector database. And then again, based on the user question, the agent would retrieve those system prompts from the database, and then it would control its behavior based on that. So the agent literally becomes better with time. And that better is defined by the user, because that's all that matters. It all depends on what the users are benefiting from. So the agent learns and adapts over time. So what happens in practice is that the user provides feedback to the agent saying that I want you to respond to emails in this tonality. The agent would actually parse that feedback from the user and then would create a system prompt and then would store that system prompt into a vector database. And then for any future user questions or prompts, the agent would retrieve the most appropriate system prompt based on the tasks. So this is how dynamically the agent can control its behavior. And going through this code example, again, I won't spend too much time here because I already covered a lot of these principles in the previous examples. So we do the same exact things. I'm not going to go through all of that. So I'm going to skip into the most interesting sections all the way down here. So this is where we define the triage router, and then we define the tools exactly the same as before. And this is the interesting bit. Instead of storing a static system prompt, we are trying to retrieve system prompts from the vector database and passing them to the agent. So this is the actual function that creates the system prompt. Again, instead of hard coding the system prompt, we are getting these prompts from the memory store. Okay, so we are fetching these system prompts from the store, and if we didn't find any, we define a default system prompt. And if we found existing system prompts or instructions, we store them into a variable called instructions_prompt, which we pass into the agent, as we can see here. Okay, so we are loading these system prompts from the procedural memory, and they're not hard-coded. Again, in the real world, what would happen is that you would get user feedback, and your application would parse that user feedback and would use that to create a system prompt that would be stored in a vector database. And any future questions from users is going to be grounded on these system prompts that are stored in the vector database. All of the code examples are the link in the description, so feel free to run them and experiment with them. The last thing I want to talk about is a very popular open source memory management framework called Mem0. So this is very powerful in implementing semantic memory, so basic facts. I haven't seen it used for episodic memory and certainly not procedural memory, but for basic semantic memory, which is actually the use case for 99% of AI agent applications nowadays, Mem0 is extremely powerful. So it can be used in the cloud or locally. So if you look at their website, they have a very nice animation. You can see that the user says, I prefer aisle seats when flying, but for long flights, make that a window seat. And then the agent says noted, and then it stores all of that semantic memory information in a database, which is a vector database. So the exact same principles that I spoke about are also applied. Okay, let me explain to you how that actually works. I think they have a diagram that explains that somewhere. Somewhere in their documentation, they explain how it works, but it uses RAG principles behind the scenes. And the nice thing about Mem0 is that it actually uses two large language models. So one large language model is used to summarize the entire message interaction between the user and the agent, and that is better for latency and cost purposes. But another large language model is used to decide what memory to be updated in the vector database. So it does that hierarchically, okay? So it can decide whether it has to override existing memories or store new memories. So that logic is actually implemented via another large language model. And if I actually go through their quick start, it's incredibly easy to implement. So you can give it a go. Very, 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 very powerful. Very few lines of code that you would have to do, much less than what you actually implemented. So if you're looking to implement semantic memory, this is a very powerful tool that I've seen a lot of large enterprises actually use in production. And going to their GitHub page, because Mem0 is open source, you can actually control a lot of these system prompts or the prompts that are used to actually retrieve the relevant documents from your vector database. So this is very useful if you are looking for domain-specific use cases. So if you work in healthcare as an example, or financial services, or anything that is domain-specific, you can actually alter these prompts to be a bit more domain specific, so the retrieval accuracy is actually much higher. And the fact that this is open source means that you have a lot of control over it, which is actually quite nice. So that is really it for the video. I hope you enjoyed this video. I hope you found lots of value from it. If you did find lots of value, please like and subscribe, share it with people who you think would find value. And with that said, see you next time.